Alright, and so in the last video we were talking about definiteness and positive, negative, semi, all that stuff. Okay, and so now we're going to talk about a theorem and maybe how it connects to that idea of definiteness. Okay, so again we have a quadratic form. Okay, so that's what this is saying. So Sylvester's theorem is saying we have a quadratic form. Okay, so quad form. Okay, and we have a symmetric matrix, and what we're going to do is look at a sequence of determinants. So kind of the first determinant, what we typically do with this sort of theorem is kind of make a box. Okay, so our first determinant is going to just be A11. Okay, then for the second determinant, we would look at this one, right? So this is going to be the determinant of A11, A12, A21, and A22. And then after that, let me do a different color here. Then we do the next one, right? And we continue until we get to, well, the whole darn thing. Okay, so dot, dot, dot. Okay, and then eventually we'll get to the whole thing. All right, we look at that sequence. And what Sylvester's theorem says, and if the determinants are all positive, so that sequence is all positive, okay, then P is positive definite, okay, as a quadratic form, okay. If the signs are negative, and actually it has to be this order, positive or negative, positive, and then negative, and then positive, so they're alternating, right? Then P is negative definite. Okay? If all are non-zero, but not a pattern, then we call it indefinite. Okay. If we do get some zeros in there, then we can't say anything. Okay, Sylvester's theorem doesn't give us any conclusion. Okay, so just a couple quick examples here. Few quick examples. Okay, so I'm going to look at the sequence of determinants here. And what I believe I find is, alright, so I get -1 as the first one here, and then I look at the second one. Okay, so 5 minus, 5 minus 1 is 4, and then I believe the whole thing has a derivative, or not a derivative, a determinant rather, of -23. Okay, you could double check that, but given the sequence, so it's negative, positive, negative, this is going to be negative definite. Okay, and for A here, okay, so I begin with this. Wait, it's not symmetric, right? So in order to do this, in order to use Sylvester's theorem, I need this to be symmetric. So since this is a quadratic form, I can make it symmetric. So -1, 1, 1, 4, 3, and then -1, -1, 0, 0. Okay, and then when I look at the sequence here, I get -1, and then, let's see, 3 minus 1, yeah, -3 minus 1, and scratch all that because I can't read what I wrote, but I forgot a -4, so that's kind of important. Okay, so it should be 4 minus 1 is 3, and then if you do the whole thing, I believe you might get a negative, or a positive 13. Okay, might want to double check that for me. And either way, it is going to be positive, so we do get that this one is going to be indefinite. Okay, no, it doesn't follow one of those patterns. Okay, and then the last one, here we get 1, and then we get 0, so then rip, we can't say anything. No information. Okay. So Sylvester's theorem can help us determine whether some quadratic formula is positive definite, negative definite, etc.